Alright, as we continue on with gluconeogenesis, once we've made our PEP, the phosphoenol pyruvate, it is going to proceed up to fructose 1,6-bisphosphate, as if we were doing the reverse reactions of glycolysis. Okay. These steps are in relative equilibrium under cellular conditions. Alright, so when we get to fructose 1,6-bisphosphate, this is the next irreversible step. Okay, and in this step what we're going to do is we're going to hydrolyze fructose 1,6-bisphosphate back to fructose 6-phosphate. And the enzyme that's going to do this is fructose 1,6-bisphosphatase. Okay, if you recall, this fructose 1,6-bisphosphatase, this is going to catalyze the reverse reaction of PFK1. And if you remember, PFK1 was the committed step of glycolysis. Okay, PFK1 was inhibited by ATP, activated by AMP in the liver. PFK1 was activated by fructose 2,6-bisphosphate, which was an allosteric activator for PFK1. Okay. And it was inhibited by citrate, which is also an allosteric regulator. When we look at the phosphatase, we'll see that it is inhibited by fructose 2,6-bisphosphate. And remember, because we're looking at gluconeogenesis, we are just focusing on the liver here. It is inhibited by AMP. Okay, both allosteric inhibitors. And it is activated by citrate. We will look more closely at its regulation in a following video. Alright, once we've made fructose 6-phosphate, it's readily converted to glucose 6-phosphate. Now, for most tissues that do gluconeogenesis, such as the kidneys and the liver, okay, glucose 6-phosphate is the final stop. The reason is that glucose 6-phosphate can be stored as glycogen, okay, and it stays inside the cell. It's trapped in the cell. If you remember from glycolysis, when we make glucose 6-phosphate using hexokinase, we trap that glucose 6-phosphate inside the cell. All right. In order to get glucose 6-phosphate out of the cell, we have to look at the last enzyme of gluconeogenesis. Okay, and that enzyme is glucose 6-phosphatase. Okay. And this enzyme is only present in tissues whose metabolic duty is to maintain blood glucose levels. Okay? So mainly this is the liver, and to a lesser extent the kidneys. So primarily you'll find this enzyme in the liver. Glucose 6-phosphate is transferred to the lumen of the endoplasmic reticulum. Here glucose 6-phosphate is hydrolyzed into glucose and inorganic phosphate by glucose 6-phosphatase. The phosphatase activity is dependent on a calcium 2+ binding protein. Once we've hydrolyzed glucose and inorganic phosphate, the glucose is transported out of the endoplasmic reticulum and then transported out of the cell. Inorganic phosphate is transported out of the endoplasmic reticulum by its own transporter protein. All right, so there are 5 proteins required to hydrolyze glucose 6-phosphate. 1, 2, 3, 4, 5. If we look at the energetics of gluconeogenesis, and I apologize for my stylus. Okay, we'll see if I write the overall reaction. We have 2 molecules of pyruvate, 4 ATPs, 2 GTPs, plus 2 NADH molecules, plus 6 waters. This allows for the formation of glucose, plus 4 ADPs, plus 2 GDPs, plus 6 inorganic phosphate, plus 2 NAD+, plus 2 protons. Delta G standard is negative 48 kilojoules per mole. Just to keep up with accounting purposes, we consume ATP when we take pyruvate to oxaloacetate, and that's multiplied by 2. We also consume ATP when we take 3-phosphoglycerate and we make 1,3-bisphosphoglycerate. So this consumes an ATP. That's times 2. Now I didn't show you this reaction because it's a reverse of a glycolysis reaction. And then we consume GTP when we take oxaloacetate to PEP. And that's times 2. So that's how we get the consumption of 4 ATPs plus 2 GTPs in gluconeogenesis. when you look at glycolysis, the overall reaction, okay, if we were to just reverse glycolysis, we would see it would be 2 pyruvates plus 2 ATP plus NADH plus 2 waters equals glucose plus 2 ADPs plus 2 organic phosphates plus 2 NAD plus 2 hydrogens. Now if you were to just reverse glycolysis as I just did, the delta G standard would be 84 kilojoules per mole. So the hydrolysis of 6 nucleoside triphosphates, okay, help offset the cost of gluconeogenesis. So we require a net of 4 additional high phosphoryl transfer potential molecules. I'll write that down. High phosphoryl transfer potential molecules to drive gluconeogenesis and make it energetically favorable.